you very much for the introduction and the invitation as well. So basically what I would like to do today is I'm going to consider the same problem as Peter presented this morning. But in this work, we're interested in the case where we are dealing with the fractional Sobolev spaces and have a practical algorithm to actually compute the Ritz representer. So the first part of the talk will be, first I will state the problem and then recall the near optimal algorithm that was presented this morning. So the first two parts will be somehow like a summary of what we've seen earlier today. And then the main part will be about the approximation of the Ritz representers. And then I'll give you some numerical experiment to show you how our algorithm perform on some examples. So the statements, we have some PDE that we would like to solve, but we don't know all the input data. And we can tackle this problem in different ways. The way we do it here is that we can alleviate this lack of knowledge, not knowing all the input data, by having some measurements of the solution. And one typical example that we have in mind is that when we don't know the boundary condition or part of the boundary condition, and here you have a picture where you can assume that we are looking at some fluid dynamic problem. We know most likely the inflow, maybe the outflow. Let's say we impose no slip condition on the top and the bottom, but maybe we don't know what should be the boundary condition that we impose in this interior boundary here. And so we would like to have a method that's having some additional knowledge of the solution by measurements. How can we actually recover the solution? So as in this morning, we will look at this model problem. So we will not consider the Stokes here, but just the Poisson problem. So minus Laplacian u equal f, posed in a domain omega. I assume omega is a boundary domain in Rd, d is 2 or 3, and I assume that it's a polygonal domain for this presentation. And f is in the dual space of H10 is known, and g, if we knew g in H to the 1/2, then we will have a unique solution, but we assume that we don't have access to g. So we cannot uniquely determine the solution to this
conjugate space?
Sorry? Oh, so yeah, good point. So this is the dual space. So every time you have a spell, that's the dual space. So basically, we want to find a solution, function in H1 that satisfies minus Laplacian u equal f in omega. Then we have access to some measurements. So we have this vector omega, which is a vector in Rm, which is lambda of u, which is the functional m different functional evaluated to the function u. These lambdas are fixed. I don't have the freedom to choose them. They are in the dual of H1, and we assume that they are linearly independent. And this is not enough. We need some extra assumption, which is usually called a model class assumption, and we assume some regularity of the solution on the boundary of the domain. And so we assume that the trace of the function u we're trying to recover is in Hs for some s larger than a half. And actually, we will assume it's in compact subset of Hs. And so then the goal is how well can I approximate u only knowing this information, so the PDE without the boundary condition, the vector of measurements, and then this regularity assumption. So I will actually further simplify the problem. I will just take f equals 0, because as we've seen this morning, this is not a key point in our problem. Because for given f, we can simply split the solution u as u0, uh. The u0 is a solution of minus Laplacian u0 equal f, and then with 0 boundary conditions. And then the remaining part will be a harmonic function, which has trace in Hs. And we'll have the measurement of this harmonic part, which is simply given by a modification of the original vector of observation. So for now, for the rest of the talk, I will just assume that f is 0, knowing that if not, then I will have to approximate also this u0, but that can be done by standard finite element approximation. So that's pretty much the goal, and as we say, we can formulate this problem as an optimal recovery problem. So basically, all that we know about the function that we would like to recover is that it belongs to this compact set here, k omega s. So k omega s is all the function in ks, I will describe what it is in a second, that satisfy the measurement. So here the omega is given, the s is given as well, and we know that U is a function that belongs to this space. And what is this Ks? It's going to be the unit ball of Hs, where as in this morning, Hs is the harmonic functions in H1 that have trace in Hs. And the norm on this space here will be simply the Hs norm of the trace of the function on the boundary gamma. So I didn't mention, but this gamma is just the boundary of omega. And here in the presentation, I assume that I don't know the boundary value at all. We could have the case where we know part of the boundary, but here we don't know the function at all. So basically, in other words, what we're trying to do is to find some function here that will be the best representative of all the elements in that set. Okay, we don't know which element here. All we know is that U is in here, and so what we would like to do is to find a point that is the best representative of all the elements. In other words, we would like to find the element that's going to minimize this worst case error. Okay, and as we saw earlier today as well, there is it is well known in that setting that actually the solution to that problem is unique. It is given by the center of the Chebyshev ball, and the worst case error is the radius of the Chebyshev ball. So the Chebyshev ball, this is, this is this B here, is simply the smallest closest ball that in H1 that contains our compact set K omega S. And then the so-called recovery error. So U is the solution I try to recover. U star is the Chebyshev center. And so we have that the error is bounded by the Chebyshev radius with constant 1. And so this is usually a theoretical tool because it can be difficult to actually compute Chebyshev centers or Chebyshev balls. But in the particular case where we are dealing with a Hilbert space, the unit ball of a Hilbert space, we actually saw that U stars can be characterized as a minimal norm interpolant and can be expressed as a linear combination of Ritz representer. So here that will be something that will be a key part in what follows. This phi j will be my Ritz representer of my measurement functionals. And so the phi j will be an element in my space Hs, harmonic with trace in Hs. That is the Ritz representer of the measurement functional lambda j when we see them as functional on Hs. Okay, so that's just the problem that my phi j satisfy. And then once we have this Ritz representer, we can find the coefficient in the expansion here by simply solving this linear system, m by m linear system, m being the number of measurements, and G is my Gram matrix, and the W is the given vector of observation. So there is a little picture here that kind of like illustrates what is happening here. So knowing the observation vector W is the same thing as knowing the projection of my function on the measurement space. The measurement space is this capital W here is the span of my Ritz representer. So if I know the projection on W, it's equivalent to know the observation vector here. And that's what I know about the U. So basically, if I fix W, I know where I'm sitting on this line here. So that's one piece of information. But then I can add anything in the orthogonal complement. I'm not going to change the value of the measurements. So if I add anything from here, then the function will still satisfy the given measurements. And we have one additional assumption is that we have a function that is in the unit ball of this Hilbert space, which is this ball here. So basically my subset K omega S is this blue line here. And we're trying to find the best representer to all the elements here, which will be the center, which is nothing other than this point, and this point is the projection of U on the measurement space. And so basically the Chebyshev center here is nothing else than the element on this blue line that has minimal norm, and it can be expressed as a linear combination of the Ritz representer, and then the coefficient are given by this solution of this linear system. And so that will be the key thing that we'll be looking at is getting an approximation, which will be based on finite elements, of the Ritz representer. Because once we have that, then we can build an algorithm that was presented as well today, which is a simplified version again because we don't have a forcing term. But the algorithm, basically, we have some tolerance epsilon. And it outputs a u hat, which is an approximation of my u star. So that's an approximation of the Chebyshev center. So basically what we have to do is to compute the Ritz representer for every functional lambda j, which is this phi j hat here. Then we compute the approximate Gram matrix. Then we solve the linear system, and then we just simply assemble this sum, and we get the approximation. And the output of this algorithm is satisfy the following guarantee. So again, the u is the function I'm trying to recover. The u hat is the output of the algorithm. And what we have is that it is the Chebyshev radius of this extra k times epsilon, where the epsilon controls how well I approximate the Ritz representer. Okay, so in other words, if I take this epsilon small enough, in terms of computation, it will mean having to do more work to get a better approximation. We have this inequality where this constant here will tend to 1 as epsilon tends to 0. And so the algorithm is called a near optimal algorithm because we don't have constant 1, but if we pay the price of more computation, we can make it quite close to 1. So again, the key ingredient in the algorithm is the computation of the Ritz representer, which, at least in the original form, requires the computation of HS in a product, which can be a problem when S is fractional, because that becomes a non-local problem. So just one slide to have a characterization, actually, of this Ritz representer. So again, I'm dropping now the indices because we apply the same strategy for all the Ritz representers. So I'm going to call lambda any of my linear functional, and phi will be its Ritz representer, and it is a solution to this system. And if you remember this space here, a space of harmonic function with trace in HS, so we can actually write phi as the harmonic extension of some psi. So the E is the harmonic extension operator. So you take a function in H1 half, gives you a function in H1 that satisfies the given G, and then satisfy this relation here for any test function in H1 0. And then the psi is the solution to this system here. So we have the HS inner product, which is an inner product on the boundary of the domain, gamma. And on the right-hand side, we have the measurement functional evaluated at the harmonic extension of the eta. And this has to be true for all the test function eta in HS. And so the main goal of this work, which is basically an extension or a specification in the case where we are dealing with fractional S, is to approximate the Ritz representer. So this is what I just said earlier. So the main goal is to get an approximation of the psi. So once we have an approximation of the psi, we can do we can get an approximation of the phi, and specifically for the case where S is fractional. And there is basically two challenges to solve this problem here. So one thing that we could do is to take a finite element space. We take a conforming finite element space for HS, and we just discretize this problem. But then there's two things. One of them is that we will have to compute HS inner products. That's one issue. And the other issue is that we will actually have to compute the discrete harmonic extension of every single basis function in the space. And so I will mostly talk about this first part here, how we can actually circumvent the fact of computing HS inner product, and then also mention briefly how we can deal with this issue here, which was also mentioned earlier today. Okay, So one thing I didn't mention so far is what is actually the norm that I'm considering on HS. And also if I come back to one thing I wanted to say here is that the Chebyshev center does not change if I change the norm. If I change the norm, basically what's going to happen, I'm going to change this unit ball, but the Chebyshev center will not change. Only the radius will change. But we have to make a choice of what is the norm that we put on HS. So we have different equivalent ways to define the HS norm for fractional S. We can have the trace norm, we can have an intrinsic norm, but we can also have what I will call the spectral norm, which is the one that we're going to use that will prevent from computing HS in a product. So for now, let's assume that the S is between 1/2. This we need to have larger than 1/2, but I also assume it's less than 1. If it's larger than 1, we can have some recursive algorithm to deal with that. I'll come back to that later. But in that setting, I can define the inner product, HS inner product, as this guy here, where L is the identity minus the Laplace-Beltrami operator. And if you think S is 1, then basically I will have here simply the L2 inner product and then the inner product of the gradient, the tangential gradient. And so that's the inner product we will consider here. I won't go into the detail how you define the fractional power of the operator. You can work with the eigenvalues and eigenfunctions and then define properly all of that. I'm not going to do that here. The key point is that now with this, my psi, which is the trace of my Ritz representer, is the solution to this fractional diffusion problem. So here you have the L, so L to the S of psi will be equal to the lambda composed with E. And one of the key points is that the mu is not regular, so mu is the composition, it is in H to the minus 1/2. But I have to, the psi now is the solution to this fractional diffusion problem that is posed on a closed hypersurface. So then once we have that, we can use the fact that we can have this integral representation of the psi, which is usually called the Balakrishnan formula. So the psi, which is L to the minus S times Z mu, can be represented by this integral here. So you have just a normalization constant. And then you have this quantity here where the y, the parameter is the parameter y. So the mu here is the right-hand side. This is exponential of y times the identity plus my operator. And we apply the inverse of that operator to the right-hand side, and then we have some constant here that appears. And once we have this representation, that is, we can actually go ahead and try to approximate this psi. Because we could remember that the goal is, at the end of the day, to have an approximation of the Ritz representer, and so to have an approximation of this function psi. So here we are still at the continuous level for now. So I just recall the formula I just mentioned, and basically if I call this quantity W of y is nothing else than the solution of a reaction diffusion problem on gamma, so on my hypersurface. So this W of y is the solution to that problem. You have some reaction part, you have some diffusion part, and then you have your right-hand side here. And to approximate that, there was different approaches to do it, but one that was introduced in this reference here is basically to use a quadrature formula. So I will apply a quadrature formula to this integral, and then once we have this quadrature formula, we'll have a reaction diffusion problem to solve for every single quadrature point, and then we use standard finite element to do that. Okay, and that's going to give me an approximation for my psi. Okay, so just very briefly, we're going to use finite elements to approximate the solution to this reaction diffusion problem. So maybe just some notation, tau h is my mesh, so I need a subdivision of my domain. And this is a mesh for the omega, so the bulk. And then we use standard Lagrange P1 finite element, so piecewise linear finite element, and I'm going to call this space VH. And it is composed of two parts, and this part here is basically the collection of the basis function associated to interior nodes, and then the VHB will be the space that is all the basis function associated with the boundary node. Okay? And so this VH0 will be a subspace of H10, this VHB will be a subspace of H1, and then I can define a space TH, which will be a standard finite element on the boundary. And that's simply the restriction of the H to the boundary, which is the same as restricting only these parts to the boundary, because basis functions that are associated with interior nodes, they vanish at the boundary, so they don't enter into the picture. Another ingredient that we will need will be a discrete harmonic extension operator. It's similar as the continuous one. It's just it takes a function in TH, maps to VH. And also we will approximate the right-hand side. So the right-hand side, I recall it's the measurement functional composed with the harmonic extension operator. And we approximate that by replacing the E by the EH. Okay. So the two steps I mentioned earlier, sinc quadrature and then finite elements, that's given here. So I have a spacing K that's going to give me my quadrature points. And then I take some two integers, positive integers that are scaling like 1 over k squared. This choice is to make sure that we have a balance of the error. I'll come back to that in a moment. But basically, we have three parts in the integral going from -infinity to infinity. So we truncate two tails, and then we have quadrature in the in-between. And the choice for the m and the n will make sure that the tails and the error inside are all balanced. And so now I have a sum from -mk to nk, and then I have this here. So basically, I will have to compute the solution w of yl for all the quadrature points. And for that, I simply use finite elements, so I replace the w by wh here, where here we simply have the finite element approximation of the continuous problems. Okay, so that's how we can get an approximation of the psi. So we'll have the psi is approximated by the psi k, so that's when I apply the quadrature, and then on top of that I apply finite elements and we get this psi kh. Okay, so one of the things that I would like to do now is to get an error estimation. An error estimation between the Ritz representer and its finite element approximation using also the sinc quadrature. So one thing that will enter into the picture will be this so-called elliptic regularity pickup index. So basically, if I have, this is this alpha gamma here, so that's an elliptic regularity pickup index for the L, where the L is this operator on the boundary. And so we assume that there is some positive constant alpha, such that L inverse is isomorphic between these two spaces here. So we have from h-1 to h1, this is for sure, but we ask a bit more. Okay, and so basically I will give a little bit of detail after that, or maybe not too much, but the key point is this result here, which is not precisely stated here, but basically the error between the exact Ritz representer and its approximation is bounded by this quantity here. The first term here is exponentially decreasing with a k, where k is the spacing for the sinc quadrature. And the second one here is from the finite element approximation, so it's some power of h. Okay, and this power t will depend on different quantities, the s, the regularity on the boundary, this alpha here, and also the another value that I'll mention later. So maybe I'll go quickly on that, but basically the idea to estimate the error, we're going to split the error that's going to contribute to the different approximation. So the full error, which is basically this, is bounded by these three terms. We have a sinc quadrature error term, we have a finite element error due to the discrete harmonic extension operator, and then the last one, we have a finite element error due to the approximation of the psi k by the psi kh. Okay, so this is the sinc quadrature. It's pretty standard. We bound the first term, which is this guy, by some exponentially decreasing term in the spacing k. And for that, we use stability of the discrete expansion operator, and then the sinc quadrature error was analyzed in many previous work. We just need to be a little bit careful because in previous work, you assume that you have a smooth right-hand side, so right-hand side in L2. For us, we have a right-hand side in h to the minus a half, so we have to deal with this less regular right-hand side. And also, we are measuring the error in h to the 1/2 and not the error in L2. So we kind of have to combine these different results to prove, but it's pretty standard. For the second one, what we have entering into the picture is this alpha that was also mentioned earlier today, is basically what is the regularity of the harmonic extension operator. So if I have a function v in here in h1/2 plus q, then the harmonic extension of v will be in h1 plus q for all the q in between 0 and alpha. So if you have a convex domain, this alpha will be 1. If you have something that has re-entering corner, you have something that is less than 1. And then the key point to estimate the second term here, which is basically the error between using E and EH, is given by this proposition here, which basically control what is the finite element error of this discrete harmonic extension. So then you can get, don't need to read through all of that. The key point is that now I give a more precise power of the H that we get in the error analysis, which involves basically this alpha omega that I just mentioned, and then this gamma, which is the minimum of these different terms, but basically it involves the elliptic regularity pickup for the L, so on the boundary, and also this 2s minus 1. Okay. So the larger the s, the larger this value here, but we are limited by the regularity that we get from the L. I don't want to say more on this. Then the last one, we get the same exponent here. And this one is basically the error between the psi k and the psi kh. And this involves the stability of the discrete harmonic extension operator, and then the finite element error for the psi k. And this is quite the technical part of the proof, so I won't say anything more on that. But we have to deal with the case we have different right-hand sides, and also estimate the error for the reaction diffusion problem, the exact one and the finite elements one. So once we have this, we have a control on the error approximating the Ritz representer, and then we can come back and have a result on the optimal recovery, which involve the Chebyshev radius plus some constant times this epsilon. Okay, so before I give you some numerical simulation, let me mention one other thing. If you remember earlier, I mentioned there was two issues. One of them was that we have to compute HS in a product, so now we deal with that. The other one was that we have to compute the discrete harmonic extension of every single basis function. Okay, and to avoid that, we can go with the saddle point formulation, where we actually enforce the discrete harmonicity constraint using Lagrange multiplier. So I mentioned that here. So this is basically what we have for the right-hand side of my reaction diffusion problem. And you see that we have to compute EH of eta H. So when we assemble the finite element system, we'll have to do that for every single basis functions. And that can be quite involved in the dimension of this is getting large. So instead, we use Lagrange multiplier. So let me maybe go back to at the continuous level. So the phi is still my Ritz representer. But we have another way to compute the phi. Instead of computing its trace and then computing the harmonic extension, we compute it directly by seeking now this couple phi and pi is the Lagrange multiplier. So if you look at this last line here, it basically says that phi is harmonic. And then this first one here basically said that the trace of phi is lambda of the extension of V. So this is the continuous one. We can discretize this, and then we can get the finite element approximation for this. Actually, with the structure, we don't have to assemble the big system. So we have this saddle point problem. We don't have to assemble this big one. We can first solve for the Lagrange multiplier, then for the boundary degrees of freedom, and finally for the interior degrees of freedom, which is the strategy that is explained here. It still involves the computation of the HS. So basically what we do, we replace that with what I mentioned earlier, which is the final basically algorithm that we have to compute the Rees representative. So we find the Lagrange multiplier by solving a standard Poisson problem. Then we solve for the trace of the Rees representer by using the sinc quadrature and finite elements, which give the same result as before. And then finally, we solve again a standard Poisson problem to get the interior degrees of freedom. Okay, so that's basically, so the same problem as we saw earlier today. Here, the goal was to get a practical algorithm for the case where we have a fractional Sobolev space, so the S was fractional. So now let me move to some numerical experiment to show you how these perform. This is the setup. So what we consider for the domain is the 2D L-shaped domain. And we will consider two different functions that we would like to recover. One that I will call the smooth one, which is the U1, and one that I will call the non-smooth one, which is this one here, which is only in H 5/3. Okay, and so if I take the trace, then the trace of U2 is H 7/6, so S should be 7/6 in that particular case. For the measurement, we will take Gaussian measurement that mimics pointwise measurements, which are given here, and I'll simply change the center Zj, which are uniformly distributed in my domain. And we don't want to deal with the sinc quadrature, so I just take the parameters here large enough so that we don't see the sinc quadrature error. So we will mainly see the finite element error. So one last word is that I mentioned that's what's happening in the case where S is larger than 1. So for now, I give the formula when S is between 1/2 and 1. If it's larger than 1, then we can simply apply a recursive scheme. If I split the S as an integer part and then a fractional part, which is between 0 and 1, then we can apply P times my operator, and then at the end, I solve a fractional problem when now the power is between 0 and 1. So I don't think I need to spend more time on that. So first, let's look at the smooth case. So what I show here is the normalized recovery error. So the U1 is the function I'm trying to recover, and the U1 hat is the output of the algorithm, where I use this strategy for a fractional S of having to use this Balakrishnan formula. And here you see the recovery error. So for instance, I consider different meshes. So every row is a finer mesh, so smaller value of H. And then this is for two different values of the S and then different values of the measurement. So if you look, for instance, S is 1. So here we don't have to solve all these reaction diffusion problem. You have the recovery error here. So now we don't see that the error should go to 0 as H goes to 0 because we have the Chebyshev radius that is there. But if we decrease H and we increase M, we should see a decrease of the recovery error. Okay, so this is what we have when we have only 3 measurements. That's the error we get. And if we go to 33, then we get some decrease of the error. What you see on top here is because actually the gram matrix is not well conditioned, and so we have this type of behavior here. But you see that as you decrease the mesh, then you tend to some fixed value, and this fixed value is decreased when you augment the number of measurements. So maybe let's look at a picture. So this is the case where I fix S, so S is 1, but I change the number of measurements. So here you have only 3 measurements, here you have 12, and here you have 33, and you have the corresponding error, and you see that you have a nice decrease of the recovery error. And then the other case we tested is that now I fixed the number of measurements M, and then I changed the value of the S. So now I have 33 measurements, and I have S is 0.55, then 1.45, and that's actually the exact solution. Okay, and so that if you take a small value of S, you have these oscillations near the boundary, which are no longer present or less present in the case where we increase this value of the S. Okay, so that was for the smooth case. The non-smooth case is pretty much similar results, so I don't think I'll spend too much time on that. Same behavior here. Then that's what is happening for the solution. So again, the S is fixed. Then we augment the number of measurements. We have a nice decrease of the recovery error. And that's for the case where we have the M is fixed, and now we change the value of the S. Okay, one thing that's maybe one last thing I would like to mention is that we are limited by the value of the S. That's something that we have to provide to the algorithm and not something that we necessarily know. What we played with is what's happening if we actually increase the S and actually go beyond the one that we're supposed to. So the S cannot go beyond 3/2, so 1.5, and in the smooth case, and in the non-smooth case is actually 7/6. That is the actual value of the S. And then we played and we went further, and you see that actually if you go further, you still have a decrease of the error up to a certain stage where actually then the error increases. And that's not something that we can explain for now, but that's what we observed numerically. Okay, so yeah, the last one is that we did a plot of the convergence for the Ritz representer. So here that's no longer the recovery error, it's just for one fixed Ritz representer looking at the finite element error. We don't have the exact solution, so we compute with respect to a reference solution. Here on the left you have when the center is at this point here, or closer to actually the corner where you have the singularity. And what we observe is that pretty much in all cases we have a rate that is close to the alpha omega, which tend to say that it is this one that we are seeing in here. There is just one that you get a better rate, but it's kind of an outlier here. Okay, so maybe to summarize, what we wanted to do here was to look at an algorithm that is practical for the case where you have fractional Sobolev spaces, and do the analysis. And in order to avoid the computation of HS in a product, we went with this integral representation of fractional diffusion problem that is defined on a closed hypersurface, and the right-hand side is something that is not smooth. But one of the nice thing about this algorithm is that it's straightforward to implement. It's basically standard finite element problem that we have to solve. And some of the things that we would like to look at later is maybe apply that to other problems. We have a code for a Stokes problem, and we have nice questions about how many measurements on the velocity, on the pressure, the interplay between that. Also, one thing is how to choose S. That's something we have to provide to the algorithm, but not something that is actually easy to know in advance. And maybe it gets some improved rate of the finite element error if you have like smoother measurements. And I guess you can add many things to the list. So I'll stop here and thank you for your attention.
Okay, so any questions, please?
Thank you, Diane, for the very nice talk. I have a question because for now you're solving the reaction diffusion problems in your finite element space. So to compute, sorry, I forgot the name, the integral formula basically. Mm-hmm. Another possible way to go would have been to diagonalize a discrete version of the L operator, so compute eigenvalues and eigenvectors for a discretized version of L, and then work with that. Could you comment on the pros and cons of this approach with respect to?
So you would have to solve the. You would have to find the eigenvalues and the eigenfunction of the operator.
And then you've got operators like some constant identity plus, and you have to take the inverse of this. Mm-hmm. You could work with the spectral decomposition, but
you will still have to compute all the eigenvalues and eigenfunctions. Yeah, so that's one thing that we avoid here. So you just solve a reaction diffusion problem, yes, for many different points, but you don't actually have to solve an eigenvalue problem.
Okay, please.
A quick question about your sync quadrature. Mm-hmm. So, broad question is, are you happy with it? But more specifically, you had a slide when you clarified the steps of the algorithm, the practical implementation of it. So, and then you said, we don't want to deal with a quadrature, so we take parameters large, m and n.
In the numerical results,
Yes.
yes.
So, does it mean that the quadrature is not a bottleneck? That the single quadrature is not a bottleneck?
So we have an exponential decay in the spacing between your points for the quadrature. So of course, the smaller, the more points you have, and so I don't know exactly how many. Maybe you can have like 200 or 400 points, which means 200 or 400 reaction diffusion problems to solve. What we did at one point was also to use reduced basis to actually, because that's just changing a little bit the reaction term. But usually what you would do, you would try to balance the finite element error and the single quadrature error. And that gives you what will be the spacing that you should use.
But computationally, it's not the hardest part of your algorithm. It's what?
Well, it's just that the smaller the spacing, the more reaction diffusion problems you have to solve. So it scales by yeah. Just.
Did you try with different configurations of the points, the data points?
So for this problem, I just take uniformly distributed in there. I didn't try to put more on the boundary or try to look at the distribution. Yeah, they were just uniformly picked there.
Any more questions? I have one. You see, there are some survey paper by Sharapudinov from Russia. Unfortunately, he died, but there is some small school, and they consider polynomial orthogonal with they called Sobolev scalar product. Like instead of usual scalar product in L201, they consider the scalar product in Sobolev space. And maybe it's possible to look if we approximate by polynomial constructed by this way. So maybe
that could be very interesting. Yeah, I'll be happy to.
They continue this research, and also in the United States there are some schools of this generalized scalar product, orthogonal polynomials with respect to this scalar product.
Okay, I would be interested to.
Okay. If no more questions, so we have afternoon tea. Not afternoon. Which one? 5 o'clock. It's written here. Afternoon tea. So thank you.